So we'll get started here with this presentation, and today we're here to talk about mission critical computing. So let me tell you a little bit about ORock and how ORock is different. So as a company, we're kind of focused on democratizing cloud technologies, and what that means is we're not going to tell customers where and how they're going to do computing. If you want public cloud capacity, we offer that. If you want private cloud capacity, we offer that. If you want edge computing capacity, we offer that. We're the only FedRAMP / impact level certified open source cloud technology provider. When we were designing our cloud, we had this thought in our minds that people are going to have distributed systems. There's no way they're bringing everything to one central public cloud. So we designed this whole system with that premise in mind. And our core focus here is to meet the demands of mission critical computing. And we truly understand what mission critical means to our customers. We feel that security, performance, and determinism are interconnected properties that you should be looking for in a cloud. So let's talk a little bit about the legacy computing model. And how this is how your traditional VMwares to your current generation proprietary cloud providers are built on. They are built on time sharing based technology. So when you buy a CPU core from a existing proprietary cloud provider, what you're really getting is a time share on a clock. You're getting 8 cores worth of time on their CPU as opposed to dedicated resources. And this is really important for mission critical computing because these cloud providers have oversubscribed their clouds, and depending on how much you pay is depending on where you're at in the queue. And for mission critical applications, you have to really start asking yourself, is it okay if my application waits to process something? If some other company paid more money than me and they come step on my workload or step on what's in my CPU cache at this moment in time, is that going to impact my workload? And in our opinion, in mission critical systems, they do not have that kind of luxury. When you ask a mission critical system to process something, it should do it right now and have a defined amount of determinism and predictability in how it processes that workload. So these are the kinds of questions you want to ask yourself when you're evaluating cloud providers. How much thought did they put into your mission critical needs? So let's talk a little bit about security in the cloud. And this applies to cloud technology. The location of the cloud is a lot less relevant than the applicable security model. We're talking about how do you secure the most basic layers of your cloud. Security, it starts all the way at the most basic premise. It starts at the most basic thing that you're really renting or buying when you go into cloud technology, and that's the CPU. So security is layers on top of layers on top of layers on top of layers in this cloud technology, and depending on how many layers are there and how your cloud provider has built their security stack depends on how much performance it costs you and how much determinism it costs you. So the things that you should be asking yourself about cloud security is what information is being shared and where, what is not being shared. And if that data was to be exposed, how would it impact my mission? If somebody came and grabbed some keys out of the CPU cache because they were using it directly after me, would that affect my mission? Would that affect my business? Those are the kind of questions you need to ask yourself. There was a very recent incident with Google that Google Drive went down, I believe on planet Earth, so worldwide outage. And a lot of people just see that, YouTube is out or Gmail doesn't work right or they can't access their Google Docs, but they don't really maybe understand the implications of how services get tied into a cloud. So Google Drive also is the back end for Nest security cameras. So if your organization was using Nest security cameras and maybe say, this is just a scenario, let's say the Chinese were targeting your organization, did they take down Google Drive just so they could walk past your security cameras without being noticed? And those are the kinds of things when we talk about mission critical workloads, the security of those workloads, the performance and the determinism are incredibly important because they could affect real things in the real world, not just your technology systems. Yeah, so let's talk a little bit about performance. And performance is really, in all actuality, what it boils down to is it's a metric of cost. Like, how much is this going to cost me? And I know that because I can measure the length of time it takes for my application to process a transaction. So I say, you know, hey, app, do this thing. I can measure how long that takes and then use that number and calculate exactly how many CPU cores I need, exactly how much time I need on that CPU. And your application's performance is called latency. So when I make a request, how long does it take for your app to process it and then give me a response back? That metric is called latency. And it's something that you should be deeply concerned with because latency adds up to how much cost you're going to have overall from your cloud provider, whether it be a CSP or whether that be on premise. It could be, you know, the number of hardware boxes you need to buy, or it could be the number of cloud instances you need to buy. But performance is a very important metric in measuring how much cloud computing is going to cost you. Because, I mean, cloud computing is pay by the cycle. So you want to know exactly how much you're going to pay. You measure your latency. So let's talk a little bit about determinism. And determinism is a term that's usually used reserved exclusively for real-time systems. And when I say real-time, I mean like motion control, safety systems, things of that nature. But really, determinism is broadly applicable to almost all workloads because determinism is how accurately can I predict what my latency is going to be? Does my latency change? And if my latency changes, that term is called jitter. So when we're talking about jitter, we're saying how unpredictable is my workload? Application, in ORock's opinion, application owners should know all the way down to the microsecond how long a request should take and how often I can process it at that speed, and have some sort of, you know, window where I know all the time my computing will happen exactly like this. And we've put this whole model together in collaboration with Intel and Lockheed Martin to deliver a system that has the highest levels of security, the highest levels of performance, and the highest levels of determinism possible, but without having to buy bare metal. So this is still enabled all the way through to the virtualization layer. So you can get that virtual machine economy. You can take advantage of all the benefits of virtualization without having to pay for all of without having to do the time sharing song and dance. These sort of parameters prevent you from having to do that time share song and dance, because what happens is application owners, they know that the system is oversubscribed, so they know that they really only need 2 cores, but they would have to get those cores all the time for their app to perform right. And since they know they're not going to get their 2 cores all the time, they're going to ask for 8. And what does that do? It drives up the cost, because everybody's asking for 8 cores when really they only needed 2 cores. And the differential in cost, the delta in between those two, is massive. And you're overbuying at every layer, at every level. Using time sharing technology puts you into the timeshare song and dance, and the timeshare song and dance makes you overbuy. So let's talk a little bit about hybrid cloud. We thought about hybrid cloud models before we started building our cloud. That's why we chose OpenStack to power our cloud, because with OpenStack, you can get that on-premise, you can get that in public cloud capacity, you can scale that all the way down to the edge, and this stuff is in production the world around. And we also want to be able to remain hardware agnostic and provide our customers with the best quality software that we can, but still maintain that deep level of compatibility in between private cloud and public cloud, because the proprietary guys are out there bolting on hybrid cloud capability to their existing public cloud infrastructure because that's what the market is demanding. Nobody's going all in on the public cloud, at least not the big guys. It's just not happening. And there's very good reason why they're not. And it's a very good reason why the whole industry is talking about hybrid cloud. But ORock has been trudging down this path for several years now. We're not trying to bolt it on after the fact. We thought about it from the get-go. So when we were building our network, we wanted to maintain control of every piece of our network. So we own our own fiber all the way down to layer 2. We believe that true hybrid clouds should all be built on one API, because the idea is that I run a cloud-ready application or cloud-native application that knows the cloud that it's on. And if I have, one technology on-premise and then a different technology in the public cloud, well, I need 2 experts that know how both of those technologies work to write cloud-ready apps, write cloud-native apps. And that developer is very expensive, and it makes your technology very complex. So let's talk a little bit about our demonstration, or getting set up here for our demonstration. And if you're a mission-critical application owner, which workload profile? Knowing nothing about workload profiles, look at these 2 graphs and tell me which one you're going to pick. Everybody's going to pick the one on the left. Why is everybody going to pick the one on the left? Because it looks very consistent. It looks very clean, and the reason why is because it's very predictable. The real word is determinism. It's very deterministic. It's not this weird blob of all over the place, which is what's happening under the hood of your cloud provider. The graph that you see on the right, that's what's happening. Unless you went and bought the most expensive version of their instance, the stuff on the right, that's what's happening with these general purpose workloads. And your existing infrastructure on premise, if you look on the right, that's very likely to be you. So with our IHS technology, the graph on the left, that's how a workload profile should look like. It should be very pointed and a very small amount of jitter and a very small amount of latency. Where the non-IHS enabled workload, you can see, this is a real graph taken from a real screenshot, that the latency is all over the place, the jitter is all over the place, and it's very hard to make a prediction on how good or not good a specific application's been written for cloud infrastructure. So now let's go on to the actual demonstration itself. So I'm going to exit out of this presentation real quick. And I'm going to show you some live histograms. And these histograms are from an operating system called Linux CNC. And Linux CNC is in production the world around to power robots. This is designed to drive real machines. And they include this tooling in here to see if your system is suitable to drive a machine and give you a profile of what it's going to look like so you know what to expect. Because when you start spinning a cutting head at 24,000 RPMs and then moving it around space and time, you want to make sure that's a very coordinated effort. So we're using these tools to demonstrate how IHS works and what kind of numbers you would expect. So you see on the graphs here, I'm going to reset these in just a minute, but I wanted you to note that, like, look at this is the base thread, and this is a third servo thread, and like I said, this is applicable to a machine controller. So this would be like how the base operating system is doing, and then here's how my actual application's latency and jitter looks like. So latency is on the y-axis of the graph, jitter is on the x-axis of the graph. So what I'm going to do is I'm going to reset these so you guys can see how quickly this stacks up in real time. And in the public cloud providers, when you go run a performance benchmark, what you're going to get is the highest performance number at a moment in time, not measured over, days or weeks, where with this kind of tooling, this is what you could do, is look at things over longer periods of time. Like this has been running so far for about 2,000 seconds. And if I let this run longer, eventually you'll see this graph over here on the right side. It will populate all the way across, and your latency or your jitter will be all over the place, both left and right. So sometimes really fast, sometimes really slow. Just depends on what's happening. So one of the things I'm going to do when I reset these graphs is I'm going to run an application called Linpack, and it's just a performance tool that tells you how fast your CPU is. I mean, it does a lot more stuff, but the most important part here is that we can get a metric, and we can also start watching to see what happens. So when I run Linpack, and so Linpack is running on both of these machines now. So the top left one is our IHS instance. The bottom right one is a non-IHS instance. The top right window is our IHS Linpack, and the bottom left here is our non-IHS Linpack. And the first thing I want you to notice is how straight and narrow the graphs are from the IHS enabled instance. That you're getting a very predictable amount of latency, and you're getting a very predictable standard deviation. And if you watch this graph, the standard deviation will actually go down as things become more and more predictable. As the workload runs longer, the standard deviation will get better. And you can watch that. If I was to reset this graph, you would see that it started at like 5, and then it will eventually work its way down to around 2 or so. But if you look over here on the right-hand side, you can see that this graph is kind of, all over the place. Sometimes it's responding really, really fast. Sometimes it's responding really, really slow. You can see that our maximum number here is in orders of magnitude. So this is the maximum latency that it took to respond to a request, where this one is very consistent at 66. This one's 18,909. So that's in orders of magnitude of unpredictability, and that's really what it gets to. Is this, looking at the standard deviation, you can see that this is a very unpredictable workload. Although Linpack does the same thing over and over and over again, I still get different results, and that doesn't make a lot of sense until you start thinking about it in a time-shared, resource-constrained environment. So this workload is running in our staging environment, and right now we have an external company coming in to develop an application against our cloud, so they're pounding this region pretty hard. They are using all the APIs, consuming lots of compute, consuming lots of storage. So that's why you see a lot of this unpredictability. And when you go to the proprietary cloud service providers, initially the numbers that you see are going to be great. They're going to be through the roof. But if you measured those over time, when that cloud got busy, you would see a graph that was very similar to this. So the next thing I want you to notice is just how much faster IHS is than standard regular old KVM. So we can run 50 gigaflops, and I'm just going to use the very first number that comes up here. 50 gigaflops for the non-IHS instance, and for the IHS instance, it's at 76. So a markedly larger number. And the longer this goes on, the more that gap grows. So, it starts at 50, and this one makes it, I think its highest number here is 80. If you look down, or if you look at the IHS one, we're up at 129. So there's a sizable performance difference. On CPU, it's more than just getting, better latency. It's also about getting better jitter and making sure that your workloads are predictable. So, because that's what it's required for. Mission critical systems is they not only need to perform good, they need to perform good all the time. So the third thing that I want you to notice on here is look at the amount of time that it took to process these. So these numbers are in pretty close alignment here, because this is the same 4 checks essentially. And that, that aligns up pretty good on here. But when we go down to the next row, we see that these numbers start to separate pretty drastically. That things start to go into the tenths of a second or into the hundredths of a second differences, where in our IHS enabled instance, it's usually only a few microseconds difference, and that's very good precision. I can build an application on that, because if I know that I'm going to have 0.07 to 0.09 second delay all the time, that it's very consistently all the time going to be that, then I can start coding applications that are timed. So safety systems that know they're going to have to wait for a specific amount of time, and they're not going to crush somebody in a door.